even though chapter 5 only has 3 sections, right, and we're the third one here, 5.3 enthalpy, the last one is a big one, right, which is why I've broken 5.3 up into 2 parts, right? This will be enthalpy part 1, and then the 4th video for the chapter will be enthalpy part 2. Right? But just be aware that even this video itself takes up 30 slides from the notes. It's a pretty big section, so feel free to break it into smaller, more manageable chunks if that's better for your learning style. But with that in mind, let's get into it. What is enthalpy? We've already defined thermochemistry as a subset of thermodynamics, focusing on the chemical aspects. And we've seen in 5.1 and 5.2 the relationships between heat and work. If we're thinking about kind of the broad themes of thermodynamics, we can consider substances, chemicals in this case, to act as reservoirs of energy. We can add more energy to them, or we can take energy away, just like a bank account. You can add money to it, or you can take money away. We store energy in a chemical substance in the form of kinetic energy. Okay? When the atoms or molecules, be it the vibration, the rotation, any way that they're moving about, is increased. Right? If we increase the kinetic energy, we increase the amount of energy that's stored in that substance. Okay? And we can consider that to be a theme called internal energy, the sum of all the possible kinds of energy that are present in a system. We call that the internal energy, symbolized as U, sometimes symbolized as E, but in chapter 5 in your textbook, we're considering it to be U. U is the internal energy. And we can relate internal energy to heat and work. Right? If we're considering all the types of energy to be heat and work, Q and W, we can define the first law of thermodynamics. Any change in the internal energy can be summed by the heat and the work. And that heat and work can go from the system to the surroundings, or from the surroundings into the system, depending on if the internal energy is increasing or if it's decreasing, which is summarized in this slide 54. How do I increase the internal energy of something? How do I make that energy go up? Well, if we're considering internal energy to be heat plus work, if I'm trying to increase the internal energy, I can do that by my system absorbing heat. That means a positive Q, an increase in heat, positive Q. It's absorbing heat from the surroundings. The internal energy would go up. Or the surroundings do work onto the system. Okay, that's a positive W. If the surroundings are doing work, increasing the work on the system. Positive Q or positive W, right? U is equal to Q plus W. If either of them increase, the internal energy increases. If the internal energy U is decreasing, that can happen in one of 2 ways. Either the system releases heat, that's a negative Q, or the system does work onto the surroundings, that's a negative W. Okay. If you're a visual learner, that's summarized on slide 55. Right? The 2 things in the top, that is decreasing internal energy by doing work, system on the surroundings, or losing heat. And the 2 on the bottom here are how we would increase internal energy, by absorbing heat or having work done on the system. Okay. Again, from 5.2, we're thinking about a closed system, hence this gray border here, where the sum of everything is 0. The sum of all these changes between the system and the surroundings is 0. So let's talk about work a little bit further, thinking about one type of work, and specifically expansion work or pressure volume work. This is how an internal combustion engine works. Right? Combustion pushes out on the pistons. The surroundings are pushing down, right? But then the system pushes back on the surroundings against a restraining pressure when the pistons are driven out, okay? Versus when the surroundings are compressing the system. Okay. So if that's going on, I can think about, oops, I jumped a slide there. I can think about the system being gas and oxygen, right? I need oxygen to combust the gasoline. And the surroundings is everything else, the engine, the pistons within the engine, the car, the universe. Now, you're probably familiar with the fact that when gasoline combusts, that's an exothermic reaction, right? It gives off energy. Heat's being given off to the surroundings, right? It's a negative Q. And the reaction is pushing the pistons out. So work is also being done on the surroundings. That's a negative W for the system. Thinking about delta U equals Q plus W, exothermic, so Q is negative. Right? The combustion is doing work, so W is negative. Both of these are negative. Delta U has to be negative. Now, what's important for us is that internal energy has a special classification. It's a type of quantity that's known as a state function. And most things are state function. Okay? What is a state function? It's something where the value depends only on the state that it's currently in. I don't care how it got there. So your altitude or your elevation is an example of a state function. If you climb a mountain, it doesn't matter if you climbed straight up from the base to the summit. It doesn't matter if you took a super windy path to get from the base to the summit. It doesn't matter if you went to a plane and then parachuted down to the summit. At the end of the day, your altitude is higher. It's whatever you are when you finish on the summit. It doesn't matter how you got there. Right? The bank account example that I just mentioned is another example of a state function. It doesn't matter if you go to the bank and you give them $4 or $5 bills, a $20 bill, or 20 singles, your account balance would increase by $20. Just like if you were to take out $100, they could give it to you in 10 tens or all in singles or 5 20s, wouldn't matter. Okay? Your account balance would go down by $100. So why is this useful in chem? This is where the idea of enthalpy comes about. Okay? Enthalpy, which is represented by the variable H, is defined as the sum of the internal energy plus the mathematical product of its pressure and volume. Okay? So this is the definition of enthalpy. Enthalpy is a state function. I can't, however, measure enthalpy values for a specific substance. I only measure enthalpy changes for a chemical reaction or a physical change. So I can't measure H straight up, right? I measure delta H, change in enthalpy. So how does this tie into what we talked about with internal energy and the pressure volume work? I didn't just talk about an engine for no reason. Typically, if you're doing a reaction or watching something occur, it's happening at a constant pressure. Okay? If you're working on the lab bench, for example, the pressure is going to be the same the whole time. So if the pressure is constant and I'm looking at a change, right, then the change in enthalpy is equal to the change in the internal energy plus pressure multiplied by the change in volume, okay, because pressure is a constant. Basically, it's just taking this previous thing and putting deltas in front of everything that would change. But we just said that P delta V, right, pressure multiplied by change in volume, represents pressure volume work. Okay? And if pressure volume work is occurring, just like in the internal combustion engine, that is negative W. Work is being done on the surroundings. So I can sub in negative W for P delta V. Right? In addition, jumping back again, delta U is equal to Q plus W. So I sub both of those things in. Okay? What I'm doing here is, if I write it out, right, I'm subbing in delta U, which we said is Q plus W. And right down here, you see at the bottom, P delta V is equal to negative W. Q plus W minus W is just equal to Q, which is what we have on the next slide here, right? Delta H, the change in enthalpy for the reaction, is equal to QP, the heat of the reaction at constant pressure. Right? And just bring your attention to the right over here. You do need to know this definition, right? That enthalpy is the heat of the reaction at constant pressure. You don't have to know the derivation that got us here from the previous couple of slides. That's just if you're into the math or the physics side of it, that's where it comes from. Okay, but know the definition of enthalpy, the heat of the reaction at constant pressure. Okay. I've said all of this verbally already. Right? The key takeaway is that the heat flow and the enthalpy change for a process are equal. Okay? So that makes enthalpy convenient for us to relate to the heat of a reaction. Okay? So that's the first important idea from 5.3. The next is to be familiar with what's known as a thermochemical equation. Okay? And a thermochemical equation looks a lot like the chemical equations we've seen already, except that they describe both matter and energy. So if I'm writing a thermochemical equation, it has to include the enthalpy change. And it's always just written off to the right-hand side. So in this case, delta H, the enthalpy change was negative 286 kilojoules. The fact that that's negative tells me it's an exothermic reaction. The other thing that a thermochemical equation must have is it has to have the physical states for everything included, and it has to be balanced. Thermochemical equations have to be balanced. But what you might notice, what might be throwing up a red flag here, is this 1/2 in front of oxygen, a non-whole number coefficient, which is weird, but it's actually okay in a thermochemical equation, because the delta H value that's given to you here is the amount of heat that's associated with the reaction exactly as it's shown. Okay? So if I have exactly 1 mole of hydrogen and exactly 1/2 mole of oxygen to form exactly 1 mole of H2O, specifically 2 gases to form a liquid, then it releases 286 kilojoules of heat. If those coefficients were different, it would change this number as well. And we'll see that that's important in the second video from 5.3. Okay. If I wanted to, and I don't like that 1/2 number, I could multiply this thing by a factor of 2. Right? It's still balanced, 2H2 plus O2 going to 2H2O, but now the enthalpy change is double what it was before. Okay? 2 times negative 286 is negative 572. Yep. If I change the coefficients by a certain factor, be it multiplying or dividing, I have to change the enthalpy as well. Yep. And I treat it the same. If I double the coefficients, I double the enthalpy. And I could multiply it by any other factor as well, 3, 4, 1/2, whatever would suit my needs. Kind of like redox when you're balancing the electrons. And you multiply all the coefficients and the electrons themselves in the half reaction method. Okay, but this is a little simpler. As I mentioned before, it depends on the physical states, so you have to include them, right? 2 gases going to a liquid here. If it was 2 gases forming water vapor, gaseous H2O, notice the enthalpy value changes to negative 242. I've alluded to this as well. If it's a negative delta H, that reaction is exothermic. If it's positive delta H, the reaction is endothermic. But what's neat is that a reaction that is exothermic in one way, if I flip it around, make all the products the reactants, make the reactants the products, right? Turn it 180, then what was exothermic one way is endothermic the other way. So notice if I flip that reaction around, it's exothermic on the top, but I flip the reactants to products, products to reactants, and the bottom reaction, delta H, is positive, 286, endothermic. It has the same exact value, 286, just a different sign. Okay. Which brings us to an example to tie together some ideas from chapter 5. tells us a gummy bear contains 2.67 grams of sucrose with the formula given right there, C12H22O11. When the gummy bear reacts with 7.19 grams of potassium chlorate, KClO3, 43.7 kilojoules of heat is produced. And we're asked to determine the enthalpy change for this reaction. Okay. Determine for what's going on right there and provide a thermochemical equation. Because this is a nice balanced reaction, okay? But 1 mole of sucrose does not correspond to 2.67 grams, which is why 2.67 grams makes 43.7. I need to do some math to find it for this reaction overall and give a thermochemical equation. This is a difficult problem. It ties together concepts from chapter 3, 4, and 5. So I recommend you pause the video and try it. See if you can get an answer. The strategy is to first calculate the limiting reactant. Okay. You're given sucrose, 2.67 grams, and potassium chlorate, 7.19 grams. Figure out, given the balanced chemical equation below, what the limiting reactant is, because that's what you'll have to use to determine the enthalpy change. So that's shown here on slide 70. Potassium chlorate is the limiting reactant. It makes less. So knowing that that's the limiting reactant, okay, 43.7 kilojoules that was produced in this reaction corresponds to the 7.19 grams of potassium chlorate, right? Specifically 0.0587 moles. That reaction, as it was written, uses 8 moles of potassium chlorate. So 43.7 was for 0.0587. I used up 8. Okay. So 8 times 43.7 divided by my 0.0587, right? This is the new thing from chapter 5. Everything before was from chapter 4. That tells me for the reaction as it's written, it produces 5,960 kilojoules of heat. Okay, negative means it's exothermic. Okay. So if I were to write the thermochemical equation, I make sure it's balanced. I make sure I include physical states for everything, and I include the enthalpy. Okay, delta H is equal to negative 5,960 kilojoules. And that is a reaction that produces quite a bit of heat. Okay? If you YouTube death of a gummy bear, you can see what that looks like, potassium chlorate and sucrose. So that's the second important idea from 5.3, okay? Knowing what thermochemical equations are and how to write them. That brings us to the idea of standard state. Okay? Usually, when we're looking at enthalpy changes, we're thinking about them where reactants and products are under the same conditions. But I want to have a definition of what those conditions are. And the standard state is defined, right? It's just all chemists have come together as a commonly accepted set of conditions to give you a reference point. Those standard state conditions are a pressure of 1 atmosphere. And if it's in a solution, it's at a 1 molar concentration. But notice there's no mention of temperature there. Those are temperature independent. Some things that you'll want to be on the lookout for, right? If you see a superscript O after delta H, right? See it right down here. That's called the knot, okay? K-N-O-T. So if you see delta H knot, that tells you that you're at standard state conditions, and you use a subscript as well to denote the temperature. So if you see delta H knot, the knot tells you you're at standard state, okay? And the 298 tells you you're at a temperature of 298 Kelvin. So those are the conditions under which you're observing the enthalpy change. You'll see that on your sapling and in your textbook as well. Okay. Where that is nice is that in having that standard state, we can look up enthalpy changes for a lot of types of chemical reactions and physical processes, keeping in mind that they have to be normalized to a per mole basis. right? You can look these things up in the appendix of your textbook, for example, but it's for the reactions as they're shown per mole, because delta H, enthalpy, is an extensive property. If I change the amount of things that are involved, I change the value of enthalpy. One of those enthalpy values that I can look up is known as standard enthalpy of combustion. Okay? So delta H, change in enthalpy, not standard state. Sub C here, that subscript of a C tells you combustion. And that's the enthalpy change when exactly 1 mole of something burns. Okay? We burn it, we combust it with oxygen under standard state conditions, and we can get the enthalpy of combustion. We've seen that enthalpy is tending to be synonymous with heat, so you frequently see this referred to as heat of combustion. Right. So take ethanol, for example. If the enthalpy of combustion of ethanol is negative 1366.8 kilojoules per mole. So that tells me when exactly 1 mole of ethanol combusts under standard state conditions, it produces 1366.8 kilojoules of heat. Right? And that's the reaction that's shown down here. See the thermochemical equation. Exactly 1 mole of ethanol, 1366. So that is what would appear in the table over here for ethanol. And we see various other combustion reactions as well. Carbon, hydrogen, magnesium, sulfur, carbon monoxide, and their enthalpies of combustion. So why am I worried about that? Yep, and these are all thermochemical equations. Why am I worried about these heats of combustion? What can I do with that? All right. Well, if I know heats of combustion, and I also know enthalpies of formation, right? What these will do is allow you to predict the enthalpy change for an entire chemical reaction. Okay? Standard enthalpy of formation, notice it's a subscript of F now, okay, is the enthalpy change for a reaction where we form exactly 1 mole of a pure substance. Okay? So here, notice it's not a combustion of CO2, but an enthalpy of formation of CO2. So delta HF is equal to negative 393. That tells me when I form exactly 1 mole of CO2, 393 kilojoules of heat is released. Right? And what's neat, if you look up other enthalpies of formation in the appendix in your textbook, the standard enthalpy of formation of any element in its most standard state is equal to 0, which is going to be key in the last video from 5.3. Enthalpy of formation of anything in its most standard state. So solid iron, for example, or gaseous hydrogen, H2, or gaseous chlorine, or liquid bromine, Br2. Any element in its most standard state, the enthalpy of formation is 0. Okay? But all molecules have values for enthalpy of formation. Some are exothermic, some are endothermic. So let's see where that's useful. Example 5.12 asks us to write a heat of formation equation, first for ethanol and then for calcium phosphate. And when you're writing a heat of formation, jumping back a slide again here, right, we write it as that molecule being formed from its constituent free elements in their most stable states. And that's the key thing to underline there. The constituent free elements in their most stable states. Okay, so if I'm writing the heat of formation equation for ethanol, I write it as being formed from elemental carbon, elemental hydrogen, and elemental oxygen. Same thing here for calcium phosphate. From elemental calcium, elemental phosphorus, and elemental oxygen. You see the answer here on slide 81. Right? To form ethanol, to form calcium phosphate, well, the first thing you have to do is think back to chapter 1 and consider these elements in their most standard state, right? Single carbon, H2 and O2, those are diatomics. Okay? Calcium, it's elemental form, O2, the diatomic. P4, right? If you remember from chapter 1, the most stable form of elemental phosphorus is P4. That's not something that would be on a test. It's one of those tricky ones. Phosphorus is P4 and sulfur is S8. So don't worry about that. But that's the first strategy. Write them out, okay? O2, H2, and C. Calcium, P4, and O2. Then include the the coefficients to be exactly what you need. So these are even easier than balancing equations from chapter 4, because you can make the coefficient whatever it needs to be. Okay? O2 is diatomic, so I have to write O2 gas. Right? But I only need 1 oxygen in my final product, so that gets a half. Versus I need 6 total hydrogens, so my H2 needs a coefficient of 3. Yep. And I need 2 carbons as a solid. Yep. Another example on the bottom there for calcium phosphate for you to think through. But be familiar with those heat of combustion equations and heat of formation equations, how to write these thermochemical equations and what they mean. Because the last video from chapter 5, the next one, 5.3 enthalpy part 2, uses all of these tools from the first video for solving for heats of chemical reactions. There's 2 ways to do it, called Hess's law, and that will be the big focus on the test from chapter 5, knowing how to use Hess's law to solve for the heats of chemical reactions.